Alright, what's up guys? In this video we're going to pick up some calculus here. We're going to do some more trigonometric integration. So we need to evaluate the integral cotangent cubed of 3x dx. So the best thing to do here is to do a simple u substitution. So the best selection for u here is 3x obviously. So we get 3 dx. We get 1 over 3 du is equal to dx. 1/3 is a constant, can be brought out, just a number. And then we'll have the antiderivative of cotangent cubed of u du. Looks like my pen is going out. Apologize about that. Okay, so now we need to integrate cotangent cubed of u. So what you can do for a lot of these trig integrals, in some cases, you can use what are known as trigonometric reduction formulas. And basically what trigonometric reduction formulas allow us to do, if we have these trig functions that are raised up higher order, they make them easier to integrate when we use a reduction formula on them. Cotangent cubed of u is not terribly big. And there is a reduction formula for cotangent. I don't have all of the reduction formula memorized. That's the problem with the reduction formulas. They're quite long and quite difficult to remember. I do have, I think I got sine and the one for sine, cosine. I think I maybe have the one for tangent memorized, but I don't remember what the one is for cotangent. Luckily for us in this case, cotangent cubed of u, again, it's not extremely big. And so if you run into a situation where you don't remember what the reduction formula is, and by the way, you will need them at some point. I mean, if you have something like cotangent to the 8th of u or something like that, you need a reduction formula for that. But again, this isn't too big. So you're going to have to go to alternative techniques if you don't have the reduction formula memorized. And honestly, I don't remember what the reduction formula is for cotangent. So what I'm going to do is I'm going to use trig identity to deal with this integral. And we're going to have to do it without a reduction formula. It can be done without a reduction formula. So we're going to use a trig identity here. So let me just remind you of a few things. So recall that tangent, this is actually a reciprocal identity. Recall that tangent theta, that's sine over cosine, or sine theta over cosine theta. So what that means is that cotangent theta is the reciprocal of that, which should just end up being cosine theta over sine theta. In this particular circumstance, I got cotangent cubed of u. So that just means that cotangent cubed of u is cosine cubed of u over sine cubed of u. So what I'm going to do is I'm going to rewrite my integrand using the following, and we'll evaluate the integral that way without having to use a reduction formula. Now again, this won't be helpful all the time if you have a trig function raised to an extremely high power. You will have to have a reduction formula in some cases to help you. But in this case, again, cotangent cubed is not very big. Okay, so now we need to integrate cotangent cubed of u over sine cubed of u du. So that may seem like we actually made it harder, but we actually didn't. We know how to deal with something like this, and we've done this in plenty of other videos. So we can break up this cotangent, or excuse me, we can break up this cosine cubed of u as cosine squared of u multiplied by cosine of u, because in the trig integral video I posted yesterday, recall that if we have the same base, which we do in this case, which is cosine, this cosine here is being raised to the first power, although it's not written, and we have the exponents here. So if we have the same base and we have exponents, we add the exponents, which means that we would have cosine squared of u times cosine to the first of u, which is cosine cubed of u. So we can rewrite the numerator this way, and we can also write cosine squared of u as 1 minus sine squared of u by using a Pythagorean identity. Hopefully you remember that cosine squared theta plus sine squared of theta is equal to 1, or sine squared of theta plus cosine squared of theta is equal to 1, because addition is commutative. So we still got our 1/3 that's on the outside here. And what we're going to do is we're just going to rewrite our numerator to make it easier to integrate. So this is going to be 1 minus sine squared of u multiplied by cosine of u, because remember we had 3 cosines up there. We only changed the cosine squared of u to 1 minus sine squared of u, so we still got a cosine up there. And then we didn't touch the bottom. That was sine cubed of u and then du. So again, go with your gut. Make sure that you work it out. Again, it may seem like we made it worse, but we're actually making it a lot easier. And we can do another substitution. Now, if you remember up here at the top when we actually did the problem, we started out with the u substitution. There will be some integrals, kind of like there are with by parts, where you're going to have to apply multiple substitutions. If you run into a situation like this, which I've talked about in previous videos, you want to do another substitution, use a different variable. You don't want to try to use the same variable again if you need to do another substitution. And just be aware of that. This will happen. That's just kind of life when it comes to integration. You may have to do more than one substitution. Again, use a different variable. It doesn't matter what you use as your substitution, your next substitution variable. It could be any letter in the alphabet, quite frankly. As long as you're following the process, it doesn't make a difference what variable you choose to do your next substitution with. Typically, after people use U, they go to V. I kind of be a little bit unconventional, and I'm going to use W. Again, it doesn't matter what you use. So we're going to do another substitution, and I'm going to pick W to be sine of U. And why do we want to do that? Well, the derivative of sine is in the numerator. So we know that if we can see the derivative in the numerator, or if we can see the derivative in the integral contained within the integral, we know our substitution works. So this would be cosine of U du, and then we need to solve for the du part, which would be 1 over cosine of U dw is equal to du. And then we're almost done. Let me go to finish this up. Put that right there. And essentially what we're going to end up getting is 1 over 3. And then we got our integral. And we're going to have 1 minus w squared over w cubed dw, which we can simplify this as 1 over 3. And then we'll have our integral. If we simplify this, this would just give us 1 over w cubed minus 1 over w integrated with respect to w, and we can go ahead and take care of that. We'll get 1 over 3. The antiderivative of 1 over w cubed, that's negative 1 over 2w squared, and then we'll have minus the antiderivative of 1 over w dw. That's just going to be ln absolute value of w plus c. Now we go back to the substitutions that we did at the beginning. The substitution that we did at the beginning was u is equal to 3x and w was equal to sine of u. That was the two substitutions that we did. So all we really have to do to finish this integral up is substitute back in the substitutions that we did. Now recall that when we substitute the sine back in, recall that we'll just basically end up getting 1 over sine squared of basically sine squared of 3x when we stick the substitutions back in, and we can use a reciprocal identity for that. Recall that that's just cosecant squared of 3x. Okay, so we'll simplify that as well. So let's just go ahead and write our final answer down. And hopefully everything made sense here. So as you can see, even without a reduction formula, we were able to get the answer to this integral. So we were asked to integrate cotangent cubed of 3x dx. And our final answer here, and I'm going to distribute as well. So we're going to get negative 1 over 6 cosecant squared of 3x minus 1/3 ln absolute value sine of 3x plus c. And that would be your solution. So let me circle that for you. And all you have to do is substitute everything back in. And all I did was distribute the 1/3 in, if you're wondering where all that came from. I just expanded out the n. Alright, so that's another trig integral. Alright, so let me know if you got any questions about how I got my answer on that one. I'll be more than happy to explain it in greater detail. I'll see y'all next time. Y'all take care.